Today what we will do, we will discuss the OFDMA system design considerations. Specifically, we will talk about the resource allocation in cellular systems. Okay. So whatever we are going to discuss now is applicable to cellular systems in general, and again OFDMA in particular also. Okay. So the issues are relevant in any cellular systems. Okay. So let us see what are those issues. What sort of issue? So when I say resource allocation, so typically it is the amount of power that you allocate and where actually the resource blocks and how many resource blocks are you going to allocate. Okay. So what are the issues, by the way? So resource allocation takes into consideration, see, allocation based on SINR, signal to interference noise ratio. In the previous class, we discussed how the cell edge user, the user in the cell edge, right? So say there is a cell here. Okay, some user who is standing here, actually he is trying to get his information from this tower, but then the interference from this tower is also a concern from him. If at all both of them are using the same resources, and this particular user, all the frequencies in a resource block in an adjacent tower may also affect him. So that is called a signal to interference noise ratio. Okay. As high power transmission, because why does that happen, by the way? Because as I discussed in the previous class, compared to this particular user who is here very near to the tower, whenever there is a person who is far away in the tower, whenever he has to communicate here, so there is a high power transmission going on. So whenever there is a high power transmission, what it is going to do is it is going to create an issue for this particular user. Okay. It's going to create an issue. It's going to cause signal to interference noise ratio. Not only, see, this high power transmission here will be affecting this particular user who are very nearer to the tower, even though they are there in the different resource blocks, but the comparative voltages, right, comparative values are going to affect them. Okay. So what can be done, by the way? What can be done? So different approaches they are talking about here. Okay, so let us see the approach, and then we will see this foolproof plan called as fractional frequency reuse. Okay, now for the timing, let us see what sort of approach they are talking about. So now let us see the bigger picture here. Say there is a tower. Okay, for the timing, let us assume the frequency reuse factor is 1. That means suppose there are 10 frequencies being used in this particular cell, the nearest adjacent cell, say, also uses same 10 frequencies. Okay. Same 10 frequencies, and here center is the tower. Okay. So 10 frequencies. Okay, or I should say in the same frequency, maybe say there are 10 resource blocks. Okay, 10 frequencies is fine. So here is your tower, and suppose there is a user in here. Say there is a user in here. So the problem is at this particular cell edge user compared to this particular user here. Say this particular user here. Okay, they say this is a mobile phone here, and say there is one more mobile phone in the a different tower. Okay, suppose both of these mobile phones, say they are allocating allocated the frequency f1. Here also this person is also f1. Since he is very nearer to the tower, he is transmitting at a very lower power, maybe. Okay, he is transmitting at a very lower power. Here also this person is also transmitting at a very low power. So when that happens, then there is less chance that the user here, this user here, is going to be affected by the frequencies from this particular tower, right? So the frequency is going to affect only when it is there in the same frequency range. If at all it is in a different frequency band, it is not at all a issue. Okay, so for those users which are nearer to the tower, it is not an issue. Okay, even if both of simultaneously 2 calls are going on in 2 towers in the same frequency. Whereas say there is a user here, say there is a user here, okay, and say there is a user here. So both of them decide to use some frequency f3. Okay, both of them they decide to use some frequency f3. Okay, Now, since this user is very far away from the tower, what is going to do is large amount of power will be allocated to him, right? Far away from the tower, poor poor signal to noise ratio. So to compensate for it, very large power allocation will be there. Then what's going to happen? So this power allocation, whatever is going to happen, it is going to affect this particular user here. Okay, it is going to affect this user here. Okay, this user here, he is going to get affected because both of them are using the same frequency band, say F3. Okay, so this is going to cause trouble. Okay, this is going to cause trouble. Even though this particular, say, I would say this particular user is here, even though he is very nearby to the, say, second tower, but still, since you have transmitted a very high power allocation here, there are chances that this power will spill in the adjacent cell, right? It will spill. Okay, so even though both the mobile phones in the same frequency band need not be there at the one near the cell edges, even though one of them is in the cell edge, one of them is very inside the cell, within the inner radius somewhere in the cell, still it is going to affect. So what can be done? What can be done? So several approaches are being suggested. One is using a frequency hopping pattern for each user. Okay, so in this particular case, what's going to happen is, so this particular tower, whatever is there, what it does, it keeps on hopping the frequency bands for whichever that are allocated. So time instant T1 maybe in this particular frequency band, time instant T2 maybe it will go to this particular band, time instant T3 maybe somewhere around here, time instant T4 maybe around here. So what here it does is, the frequency allocation for this particular user, it keeps on changing, say F1 maybe, then F8 maybe, then F3 maybe, it keeps on hopping, so that the user which was going to affect earlier continuously by this particular frequency, say only one frequency F3 was being used here. Okay, F3 was being used here, then the high power would have caused a signal to interference ratio. But then they see the frequency is kept on changing. The frequency resource allocated is kept on hopping. Okay, just like in your frequency hopped spread spectrum maybe. Okay, you can the same, the data is being carried by different frequency blocks during different time instant. Then what's going to happen? Maybe for a fractional time instant, he is going to be affected by the signal to interference ratio, but otherwise maybe 1/10 of the times only is going to affect it. Remaining 9/10 of the times is free. Okay, so that particular approach actually was called as Flash OFDM, and that particular company, some Flareon, some company, it was so in thing in 2013. Then the company was taken away. It was bought by the Qualcomm, the leaders, and then anyway, the thing was much complicated. There are better ways to handle it. But anyway, it was an approach which was discussed. Randomizing the frequency allocation, right? Frequency hopping. Okay. It was a load on the base station though. Because the thing cannot be applied for single user, but rather it should be applied for all the users. Okay. This was one. What can be the second approach? The second approach can be having a master scheduler. Okay, having the master scheduler in the sense what? So for this particular scheduler means, suppose I have one tower here, say there is third tower in this particular range. Then suppose all these three towers are being controlled by one more tower here, say one more control station here, so that this particular control station knows exactly which users are there at the cell edge, which users are there in the cell center, and which frequency allocation to this particular user might call a issue, and to avoid the situation. See, first of all, we are telling that there is a lot of burden on carrying the metadata, right, other than the actual data. And now we are talking about having one more controller to control all the frequency allocation in the individual tower. So that was a big ask. So this particular, yes, possible, and it was a suggested solution, but then too complicated. Okay, so having a master scheduler which knows, right, which all frequencies in which all cell users case are going to create troubles, and avoid the situation by allocating a smart resource block in a smart manner. Okay, so that was the second idea. But then there are better methods that have been employed. Let us see. Okay, so the best method, by the way, that are being used is fractional frequency reuse. Okay, so fractional frequency reuse, you might remember when I said the cellular communication, the whole reason why cellular communication was suggested, the reason why cellular communication was suggested actually was the frequency reuse factor. Okay, actually when it was suggested, if the idea was, say there is a tower here and there is a tower here, if both of them are using sufficiently low power transmission, then say I have say 10 frequencies at my disposal, then by splitting the entire tower area into say three smaller areas with a lower power transmission, I can use 10 frequencies here also, 10 frequencies here also, and the same 10 frequencies here also, right? But then we know what caused the problem here. This is the case where cell reuse factor n is equal to 1. Maximum utilization. Okay, maximum utilization, highest throughput in the sense that all the blocks in first one at a time, this could handle 10 calls in the first cell, 10 calls in the second cell, 10 calls in the third cell with the same 10 frequencies at your disposal. But then what was the problem here, by the way? Here actually the SINR, right? Signal to interference noise ratio problem was very much dominant here. So that is why the suggested solution was that we go for fractional frequency reuse. So what to do with how to manage this fractional frequency reuse? See here, this is two options are being suggested here. In the first approach, you can see, suppose I have 4 set of frequencies at my disposal. Now you can see suddenly, okay, now the same set of frequencies, whatever you are going to use, now also you have the freedom, but you are using the same set of frequencies only in the inner radius where the tower is situated. Okay, only in the inner radius. If at all there is a user here, he will not be allocated the same frequencies which might be there in the adjacent cell. Okay, suppose this particular user is here. You can see here, now the user and here, your minimum distance is being maintained. See here, now the distance. Okay, if at all I have to represent this with a conventional cellular communication with cell frequency reuse factor of 1, then maybe I would represent it by all 3 of these hexagons with completely black. Okay, I would represent them with a completely black color maybe. But here you can see what has been done. The inner circle only. Okay, only if at this particular distance. Okay, that means whenever these particular frequencies are being used, it transmits them with very low power. Okay, then suppose if at all there is a user here at the cell edge, he is not being allocated this frequency, rather he is being allocated with this particular frequency. You can see this user here is being allocated with this particular frequency, and this frequency, the nearest place where this particular frequency is again going to exist is here. Okay, the nearest place where this particular frequency is going to exist is probably in this particular range here. Okay, similarly this particular user here, say there is a user here, the nearest place where this particular frequency will be used once again probably would be somewhere around here. Okay, so the distance has been increased. Okay, so the distance has been increased. By doing so, the frequency, the signal to interference ratio has been improved. Okay, but what is the problem here, by the way? The problem is the efficient utilization of the resources. Now you can see out of every user, whoever is allocated here, you can see these particular frequencies in the normal conventional cellular communication, all the frequencies would be used here, but these frequencies here, they are being used. Okay, say these 3 frequencies are being used only when the users are at the cell edges. Remaining all other times they are not being used at all. So the efficiency of this particular scheme is very low. I would say the throughput, right? The efficient throughput. That means out of the frequencies, whatever you purchased in a bid, how many are being used currently? Not much. Okay, because so this is fine, you are getting the advantage of cellular communication, but then not exactly, not exactly. So efficiency is poor. So one more idea that was suggested, okay, something that was better than you know this, but then it was a compromise to increase the frequency capacity. Here only one frequency is being used efficiently. Even this frequency is not being used. This is being used at a efficiency of maybe say 80%, and all these frequencies are being used at an efficiency of 15 or 20% maybe. So the other option was something called as soft frequency reuse. This thing was called as strict fractional frequency reuse. Makes sense. Okay, makes sense, because the nearest users are being separated. Here in this particular case, what they did was, in the center also, they could use two sets of frequencies. You can see two sets of frequencies they could use, here also, and here also, so that those frequencies, you can see F1 and F2. So all of those frequency bands will be utilized up to say 35 to 40% efficiently. And then near the edges, the distance also can be maintained. Okay, near the edges also distance can be maintained. Now, is it safe? By the way, here you can see white. Okay, so this particular frequency F3 is at a distance of, you can see this particular shaded region, it doesn't contain F2 and it doesn't contain, yes, it contains F3, but the distance has been somewhat better. Okay, you can see this particular distance of this particular frequency. Okay, say there is a user here. Okay, he is getting the actual information from this tower, and he is going to get some interference from this tower also, but you can see the distance is maintained. Okay, there is some distance that is being maintained. So this particular distance, if it was a conventional cellular communication with cell frequency reuse factor of 1, it would have been 0. This distance would have tended to 0. Whereas in this particular case, the distance was almost double. Here the distance has been half. Okay, the distance has been half, but then you are using not 4 set of frequencies, but only 3 set of frequencies in a multiplexed manner. So you have made a compromise, but and the throughput also is somewhat better. Okay, so soft frequency reuse is a method in between the strict fractional frequency reuse and the conventional cellular communication. Okay, so now let us see the graphs. Okay, what graphs? Usually graphs have a better way to communicate. So you can see here cell edge users performance as and when the interior radius, okay, radius from the center of the tower center to the cell edge user, as and when it increases, the signal to interference ratio is getting worse. By the way, okay, it is much worse. Even at the center, even it was center, it was worse, and as you go towards the edge, it was getting much worse in case of no frequency reuse. Whereas in case of strict frequency reuse, it was very good. Okay, even the one at the cell edge user was not suffering because the distance was double, right? We saw in that particular case. Here is an intermediate solution, because what are the odds of users being there near the cell edge, and what are the odds that all the cells will be used simultaneously? Okay, so based on the probability thing, so maybe worst case scenario will be you will be there in this particular range only. So this was a intermediate solution. Okay, what about the spectral efficiency? Spectral efficiency, as I told, whenever you go for the conventional n is equal to 1 case, all the frequencies in all the cells will be used maximum at a time. All say calls come 30 conversations going on, 1 in each, 10 in each cell, entire all the resource blocks will be simultaneously allocated. But here what's going to happen, suppose there is a user here in this particular block. Okay, say there is one more user in this particular block, and now okay, let me take you to the previous page here. So what's going to happen in this particular case is, now say there is a user in here, okay, and there is a call going on. Then say user is here, then you can resource block can be allocated. But if at all there is a user here, then you can allocate how many resource blocks? See, even though there is a potential in F3, you can only allocate maybe some like 20% of the resource block. Remaining resource block cannot be allocated, right? Remaining resource block cannot be allocated because what are the odds? Okay, so that was the case. So in this particular thing, the throughput, if at all you consider in case of subcarrier allocation, which more the subcarriers allocated, higher the subcarrier occupancy, better will be the throughput. So the spectral efficiency in case of the conventional cellular communication was very good, but unfortunately not so in case of strict frequency reuse, whereas soft frequency reuse you can see is a intermediate solution. Okay, so this is one way of handling the resource allocation. Okay, so two things we saw, right? One was the clever power allocation, larger far away the mobile phone, whatever it is, more power you allocate so that the SNR is better. Closer it is, lesser power. That was the one approach. And second one is frequencies, how they are allocated. Okay, how they are allocated. Now the next discussion is on the multi-user diversity, and going for each of this diversity, is it going to add up to the total performance, or is it like if at all I use multi-user diversity, I cannot exploit much from the frequency or spatial diversity, or it's just like if at all I use spatial diversity and frequency diversity, there is not much of a gain coming from multi-user diversity. So the second case which I told is true. Just because you go on using all the diversity techniques, the advantage do not keeps on, multiplying. The gain due to individual diversity do not keeps on multiplying, but there is a catch involved. Okay, so exploiting one of the diversity is going to nullify the effect of the other diversity. That's what the author is going to tell here. Okay, so by the way, let me just ask you, what is meant by multi-user diversity? What is meant by multi-user diversity, or what is meant by frequency or spatial diversity? Will somebody tell me? Okay, so what did I say? Okay, then what is meant by free? Okay, so the spatial diversity, once again, let me tell you. So did you get this thing? So one transmit antenna and one receive antenna. Say I have, if at all there is a single channel, if the channel is bad, say if the channel is very poor, then what's going to happen is I will be settling for, because of poor channel feedback, I will be going for maybe 16 com. I will settle for 16 com with rate half code, so which is of very poor throughput. Instead say I go for one transmit antenna and say two receive antennas. Then what's going to happen is, suppose first channel is bad, whereas my second channel may be good, then I will skip this particular first channel from the first antenna. I will use this particular channel where situation is good, and I will use maybe 64 com and maybe rate 3/4 punctured convolution code. So my throughput is very good. So this is called as spatial diversity. Okay. Now what is meant by frequency diversity? What is meant by frequency diversity? So in frequency diversity, suppose this is my entire frequency band, and say instead of using the single very large bandwidth, say for a particular user, I have decided to use pieces. I will allocate them different pieces here like this. I will cut them into pieces. So what's going to happen is, in place of a very large data that you are going to transmit, say suppose your channel was suffering defades in a particular places, say maybe here, then what's going to happen? This particular case where you have split the entire data in the entire frequency band in a randomized location, then you can see there, since the frequency was not the data was not there in this particular band, but it was spread, you are going to employ very high speed communication, maybe with less number of losses, and you are going to achieve frequency diversity. That means instead of sticking to the same location, say I transmit the data through, by spreading the data on the entire frequency bandwidth on a larger location, I get a advantage. That is called as diversity, frequency diversity advantage. Now let us talk about what is this multi-user diversity. Multi-user diversity is a case where, say there is a single tower here, there is a user 1, say there is a user 2, say there is a user 3 here. Okay, unfortunately on some fine day, out of these 3 users, suppose this particular user here is having a very poor signal to interference ratio characteristics. Even this particular user is going to have very poor signal to interference ratio characteristics. Only this particular user is having very good SNR properties. Then what's going to happen is the entire throughput. Then what the tower can communicate with this user only with a very nice speed and very nice throughput, whereas the path between the tower and this user and tower and this particular user is going to be very poor. So entire throughput is going to dry down. What if, but see here in this entire space, I considered only 3 users. Okay. I will now stop. Okay. We'll conclude this. Okay. So in the entire band, there are only 3 users. So what's going to happen is there are chances that only 20% or only 30% of users get a good channel. Remaining 70% users will get very poor channel. Instead, say I have 50 to 60 users everywhere, 50 to 60 users everywhere densely. Okay. Then there is a chance that most of the users will suffer, will have a very good channel status, whereas only 10 or 15% of the users are going to have very poor channel responses. Then what's going to happen? Just because many users are there, most of them will get the advantage of high throughput and very few of them will suffer poor throughput. But overall, from the tower's point of view, multi-user diversity is going to increase the throughput. That means more the number of users, better will be the throughput from the tower point of view, not from the individual. Individual is going to suffer because more the number of users, more signal to interference ratio. So tomorrow we'll conclude this and we'll start the next topic. Okay. So thanks for joining. Everybody just say hi and let us quit. Everybody just say hi and you can go to HOD's class. Okay.